Well, welcome to the iodine clock experiment, and in this experiment we're going to look at a way to measure the rate of a chemical reaction. We're going to examine how changing concentration can allow us to determine the order of reactants in a chemical reaction for the rate law. We're going to study the effect of temperature on the rate of reaction, and study the effect of solvent polarity on the rate of reaction. So the iodine clock reaction involves two separate reactions. The first is the main reaction between iodide, I-, and persulfate, S2O8, 2-. And when these react, they form iodine. But we want a way to measure how fast this reaction proceeds. So what we do is we add in thiosulfate, S2O3, 2-. And thiosulfate reacts very quickly with iodine and reforms iodide. So in other words, no iodine will exist in the solution until all the thiosulfate has been used up. When all the thiosulfate has been used up, we have starch in the solution, and the iodine will complex to the starch and turn blue. Therefore, if we measure the time taken for the reaction mixture to turn blue, we know how long it took for the thiosulfate to be used up. So the thiosulfate is acting as a clock. It's measuring for us how fast the reaction proceeds, how long it takes for the thiosulfate to be used up. So here are the range of solutions we're going to be using in our iodine clock experiments. In the first three experiments, 1 to 3, we're varying the concentration, either of the iodide, I-, or the persulfate, S2O8, 2-. You can see in going from experiment 1 to experiment 2, we've doubled the concentration of the iodide, but kept the persulfate constant. In going from experiment 2 to experiment 3, we've kept the iodide constant, but halved the concentration of persulfate. Note through all of the experiments, the concentration of thiosulfate, or clock, is the same. 1 milliliter of 0.01 molar solution. This means that we can measure the rate, as we'll describe later, by looking at the concentration of this species and its relationship to the concentration of persulfate. We then have temperature-dependent studies, where we're going to repeat experiment 2 again at 0 degrees or close to it in an ice bath, and in a warm bath, for example 40 degrees. So we'll have three temperatures: room temperature, a cold temperature, and a warm temperature, and we'll be able to measure the rate and rate constant for each of these three. Finally, we'll look at the effect of solvent by removing the potassium nitrate, the ionizing solvent, and replacing it with the ionized water. So this is our experimental setup. We have burettes to deliver our volumes, and we're going to have two solutions. In beaker A, we're going to have our iodide, one of our reactants. We're going to have thiosulfate, which is the solution that's going to mop up the iodine as it forms. We'll have potassium nitrate, which ionizes the solution, and we have starch indicator, which will go blue as soon as our reaction has used up all of the thiosulfate. It's very important to deliver very accurate volumes, especially the thiosulfate, because we're measuring the time taken to use that up. So if the volumes aren't accurate, the times we measure, there'll be a large error in those times. In our second beaker, we're going to have the persulfate, our second reactant. So we'll have two beakers, and in each experiment we're going to mix beaker A with beaker B. So our first set of experiments is going to be studying the effective concentration. So in experiment 1, I've measured out 1 ml of iodide into my 1A flask with the other reagents, and 5 ml of persulfate into my 1B flask, and now I'm mixing them. On mixing them, we start the stopwatch, and now we're going to measure the time taken for the solution to turn blue. So here I've fast forwarded through time, and you can see at about 3 minutes 20 seconds the solution turns blue. This is the length of time required for the thiosulfate to be used up. We just need to check our temperature, and our temperature is 290 Kelvin. The reason we do this is we want to make sure that the temperature is the same for all of our concentration studies. In my second, it's the same as the concentration of the iodide. The persulfate is the same, so I'm changing the concentration of the iodide, and I want to see what effect does this have on the rate of reaction. So I mix my solutions again, start the stopwatch on mixing, and measure the time taken for the solution to turn blue. So, fast forwarding through time again, you can see we're at a much shorter time now, and the solution turns blue at around about the 1 minute 50 second mark. So we've doubled the concentration and the rate has doubled. The time taken has halved. We were 3 minutes 30 in experiment 1, now it's 1 minute 50. So doubling the concentration in this iodide has had the effect of doubling the rate of reaction. Our temperature is the same as before. In experiment 3 it's the same as experiment 2, except now I'm halving the concentration of persulfate. And I want to see what effect does halving the concentration of persulfate but keeping the iodide constant as experiment 2, what effect does that have on the rate? So we mix our solutions. You know, we always pour back and forward between the two beakers once, just so we get good mixing. So fast forwarding through time again, and you can see now we're at much longer time, so halving the concentration has had the effect of slowing down the rate. So persulfate must be involved in the rate law, and the solution turns blue at about 3 minutes 27 seconds. So this is exactly the same almost as solution 1. So halving the concentration has halved the rate. We were at 1 minute 50 in experiment 2, is now gone to 3 minutes 20. So if we look closely again, experiment 1 to experiment 2, we doubled the concentration of iodide and the rate doubled, or the time taken halved. In going from experiment 2 to experiment 3, we halved the concentration of persulfate, kept the iodide constant, and the rate halved, at the time taken doubled. So we can derive information about the order of reaction with respect to iodide, N, and persulfate, M, from these experiments. Knowing this information then, and knowing the reactions that take place, we can calculate the rate constant K. The concentration of thiosulfate, our clock, was 5 by 10 to the minus 4 molar, if you look at our reagents. When we look at the balanced equations, we see that the concentration of persulfate is half this. It's a 1:2 ratio, so therefore the rate of reaction, the rate of consumption of persulfate, is 2.5 by 10 to the minus 4 divided by the time taken for the solution to turn blue. Once we know rate, we know our concentrations, we know N and M from the concentration studies, we can calculate K. We've said that the rate is dependent on temperature, so here we're going to do an experiment at lower temperatures. In this case I have my solution sitting in an ice water bath, and the temperature of the solutions is 276 Kelvin. This is experiment 2 again, so at room temperature this was about 1 minute 50 seconds, and you can see in an ice water bath it takes much longer. The reactants have much lower energy at this lower temperature. So we see here we have a time of over 3.5 minutes for the mixture to turn blue. We can do it at higher temperatures as well. So here we have a water bath. I've set it to about 35 degrees. So I have my solution sitting in there for about 10 minutes. I'll measure the temperature, and we see here the temperature is about 32 degrees Celsius, or 305 Kelvin. We'll mix our solutions. Again, it's experiment 2, so I'm keeping everything constant. We have 3 experiment 2s now, one at room temperature, one in an ice water bath, and one at 40 degrees Celsius. And we're examining the effect of temperature on the rate of these reactions. So we saw when we cooled it down, the rate very much slowed down. The time taken was much longer. Now we're heating it up, and we're watching this in real time, and we'll see obviously that the rate is going to be much faster, the time taken much shorter. We can use this temperature dependent information by calculating the rate constant K as before, and using this value K in the Arrhenius equation. The linear form of the Arrhenius equation is natural log K is equal to natural log A minus EA over RT. EA is the activation energy. This is a linear equation, so if we plot ln K versus 1 over T, our slope will be minus EA over R. So we can derive the activation energy from the slope. Finally, in all of the experiments so far, we've had potassium nitrate in our solutions. In this case, we're going to remove the potassium nitrate and replace it with deionized water. So what we want to examine here is the effect of removing the ionizing solvent. And if we think about the nature of our reactants, iodide and persulfate ions, these are both ions. So in an ionic solution it's going to be much easier for these ions to collide. So therefore if we remove our ionic solution, we can see here the time taken is much longer. It was 1 minute 50 with the ionic solution present. Here now it's about 3 minutes 27 seconds. So therefore the ionic solution helps the reactants react faster and our rate is faster.